Hello.
Hello, Mick. I'm Fedor, your assistant.
Okay. Hello. Nice to have you here. Or nice to be here.
Hello, Mick. I'm Fedor.
Have you received any information about the speakers? Will everybody be joining us, or? Have you received any information about the speakers? Will everybody be joining us, or? Speakers. Will everybody be joining us, or?
Dear Mick, can you repeat, please?
Have you heard anything about the speakers or the ones who should present in this session? I haven't received any emails. Actually, I just found the email regarding this session today morning. Have you heard anything about the speakers or the ones who should present in this session? I haven't received any emails. Actually, I just found the email regarding this session today morning.
I have a little trouble with sound. Everyone speakers here and ready to enter.
Okay.
I have a little trouble with sound.
So probably you can let place the first speaker in so that we can start on time. Probably you can place the first speaker in so that we can start on time. Okay. Hello, everyone. So I think we can probably proceed. So it seems that we have everybody are here, so we probably have all the presentation in this session. So for those who are following this on YouTube, so welcome to the POAC 2021. My name is Mikko Suominen. I'm from Aalto University, and I act here as a convener of the session. And this session is about mechanical conditions and ice strength, part 1. And first speaker is Riikka Matala. Topic is the effect of ice fragment shape on model scale brass ice material properties for ship model testing. So please, Riikka, go ahead.
Good morning. My name is Riikka Matala, and I'm very happy about this opportunity to present our work in this online event, despite all the difficulties going on in the world. Can you hear me? Any comment?
Yes, we can hear you.
Okay, very good. Okay, can you see my slides? No, probably not. I think you are seeing my notes, is that correct? Sorry. Are you seeing my slides?
Not yet.
Okay, then I need to do something. Just a second. Ah, now I understand. I think this says that the host is displayed my screen sharing. Can we do something about it? I'd like to share my screen or my slides.
Pedro, can you do let Riikka share the screen, her screen? Probably you can try now, Riikka.
Okay, thanks. Oh, yes. Here. Can you see it now?
Yes, now I can see it.
Very good. So let's start over. Okay. Okay, so still like this. Okay, let's start over. So my name is Riikka, and I'm presenting my and my colleague Hanyan Gong's study on the effect of ice fragment shape on model scale brass ice, focusing on its possible influence in ship channel model testing. Our presentation starts with introducing the background of the study, that is how we understand the old channel brass ice fragment shape and why we wanted to study it more. After this, we outline the methods used for describing the fragment shapes and the fragment shape relation to granular material properties. These topics, 2 and 3, are mainly utilizing the experiences from soil mechanics. The following part proposes a simple method for characterizing model brass ice shape using computational geometric methods. Finally, we assess the particle shape change influence on the brass ice behavior. My personal interest for this topic has developed while I have been working closely with ice model testing in Aker Arctic Ice Laboratory. I think model testing is a valuable tool in ship design. However, nowadays the ice-going vessels are not typically icebreakers breaking through level ice, which was important, of course, in the late 60s, when the model testing was first established. Instead, today there is a wide range of different demands for ship performance in ice. I really find it important to keep the model testing procedures up to date so that they can reliably serve the ship design work also in the future and evaluate the ship performance accurately in relevant ice conditions, including broken ice conditions. An old brass ice channel is especially important as the vessel ice class can be granted based on brass ice model tests. Old channel is a typical condition for a merchant vessel in the Baltic Sea, and it forms when multiple ships are piloted through the same channel. As a result of several ships passing through the channel, the shape of brass ice fragments become less angular and solid due to repeated freezing cycles as the ice fragments are spinning in the water. As mentioned before, the Finnish-Swedish ice class rule provide guidelines for verification of ship performance through model testing. We have a research on the topic going on. Earlier In our research, we aim to assess model ice initial strength influence on model press ice properties. Related to that research, we noted that the Finnish-Swedish ice class rules do not currently specify the press ice fragment shape. As the difference between angular-shaped ice fragments in ice ridges and less angular-shaped ice fragments in an old channel is often mentioned in the literature, we wanted to assess if the shape is a character that should have a target value for model testing. Press ice is commonly understood as a floating accumulation of round ice fragments. In this sense, the material can be considered as floating granular material. We saw soil mechanics as a decent starting point, as it has a long tradition in describing, measuring, and characterizing different materials. Well, does the shape matter? According to soil mechanics, both particle size distribution and shape influence granular material response. Traditionally, more attention has been given to particle size distribution than to particle shape. This seems to be a consequence of the size distribution being more simple to measure, whereas describing the shape requires more complex methods. In soil mechanics, the particle shape has been described using qualitative and quantitative methods. Traditionally, the qualitative approaches describe the shape with simple descriptive words, such as spherical or flaky. The quantitative description is based on geometrical measures. The quantitative method is reproducible and therefore preferred by the field engineering. However, both descriptions are experience-based approaches. Unfortunately, the terminology of shape characters has not been standardized among the different fields, such as geology, mathematics, computer science. The good news is that the term seems to describe the similar characters, while the exact determination formula might not be standardized. For example, sphericity means circularity and roundness describes the angularity. In our earlier research on vessel channel resistance, we have been using a set of easy to measure press ice properties, which we in the first place believe to influence on ship resistance. These properties are porosity, internal friction angle, angle of repose, and property we call compressibility. This slide summarizes the relations established within soil mechanics for these properties and shape factors. Porosity was found to be depending on sphericity as a consequence of the particle rearrangement, which is simply filled here in the picture. Basically, all the properties, including porosity, were influenced by the particle angularity or the surface characteristics, namely the fragment roundness. This is why we chose to use roundness as the key shape attribute in our final analysis. According to this table, the fragment shape could influence all the considered properties. Later, we assess whether this relation is significant in practice in model testing or not. These empirical formulas presented here will be applied in the latter part of this presentation to evaluate model press ice. However, it should be noted that these formulas are empirical formulas, which are detected based on tests on different soils. Now we have outlined what the soil mechanics has to say about the shape determination and the properties interesting for our press ice research. Moving on now to the case study we run with model press ice samples. 3 comparative sets of model press ice were evaluated in terms of the test repeat and shape characters regarding sphericity and roundness. To be able to do this, we propose a simple approach to characterizing model press ice shape by digital images. Each test day, the first press ice sample was collected before a channel model test. This sample is called new channel in the study. After the ship model test, the press ice is collected back in the channel and the ship test is repeated twice. Such press ice channels are called here old channel 1 and 2. The samples are taken from the press ice always before the ship test. The press ice is considered to potentially lose the initial material properties after the ship test, and this is the reason why we studied the influence of repeated channel test. The press ice sample was set on grid panel and photographed. MATLAB image processing toolbox is used to post-process the ice shape in images. The sample image is converted into noise-filtered black and white binary image with adjustment of overexposures. Here you can see both the original photo and noise filtering image. Let's now focus on the experiment results. First, we consider the test results regarding the sphericity. So the above figure is an example of test sample one analysis showing the detected sphericity values. Idea is, after all, to evaluate how closely each fragment shape resembles a circle. The figure below presents each sample sphericity value probability distribution. From this data, we can see that there is more differences between the ice samples. It seems that the sphericity of the used model press ice decreases when the channel test is repeated. If we now turn to roundness, we can see small but existing differences between the samples. The sample 11 to 13 were made of weaker ice, 25 kilopascals in the model scale instead of 50. And that sample fragments can be seen to become less angular when the channel test is repeated. This indicates that the soft ice sharp corners can easily be milled away by the press ice fragment interaction. This slide describes the pathway used in this investigation to assess the press ice fragment shape possible influence on ship model testing. We use the roundness value as basis for this analysis. First, we take the data from the case study and calculate each model press ice sample mean roundness and see how much there is variation in the sample from repeated tests. After this, we utilize the soil mechanics empirical formulas and find out what would be the influence of roundness change in the press ice or the properties. For curiosity, we also calculated how the same press ice properties would change if the shape would change from very angular to completely round. We admit the assumptions are quite heavy, especially the two assumptions mentioned here. First, is it appropriate to directly apply relations determined based on soils? No, as press ice has unique granular material characters, such as relatively weak ice material strength and temperature dependency. The material weakness is especially an issue in model ice, which is scaled using Frude scaling law. However, in nature, press ice fragments are often considered strong and solid, which would better justify this assumption. Second issue is the exact determination of roundness, as the terms are not standardized. However, the roundness definition is the same, describing the fragment's angularity and the surface roughness. So here we go. What we can see here is that the observed fragment shape changed in any model press ice sheet would not significantly alter the studied material properties. By comparison, the reference values of fragment shape roundness varying from very angular to perfect round would substantially affect the studied material properties. Assuming the press ice in full scale behaves similarly to granular soil, the effect of roundness on the material properties would be pronounced as the reference values indicated, such as porosity here changed by 26%. As a summary, it seems that repeated ship model testing slightly changes the model press ice sphericity and roundness, but this change would not significantly influence the considered model plus ice properties. The fragment shape roundness varying from very angular to perfect round would, though, substantially affect the considered plus ice properties. As a conclusion, the press ice fragment shape changing from angular to round would significantly influence the material behavior. In my opinion, it would be fair to consider including the fragment shape as a target property at some level for ship model tests. Mainly, this would be to secure the test repeatability and standardized test outcomes. So this was my presentation. Thank you for your time. Now I'm looking forward to hear your thoughts.
Thank you, Riikka. Really nice presentation. It seems that the YouTube is coming a bit behind, so probably have to wait a little bit for the possible questions. But if any listeners have any questions, please go ahead and post your questions. In the meantime, I could probably ask that one question that you showed the picture from with this red surface and against the red surface, and then the MATLAB processed image. It seemed that at least some part of I would guess it's some sort of slush that was not included in the picture. Like here, you can see that some of the slush is not included. So did you have some sort of threshold for what size of pieces you would include in this? I mean, when you did this MATLAB size detection or roundness detection, did you just had some value that below that you didn't include the particles?
Yes, sure. There was some threshold which I can't really recall right now. You are correct. This analysis is not able to catch all the slush, which is also visible in this picture. In my opinion, this slush has quite remarkable influence on the channel resistance, but at this point we kind of just excluded it from this analysis.
Okay, thank you. I guess there's no further questions, at least in YouTube it seems that there's no questions, so thank you for the nice presentation. And then we can go ahead and to Andri Murcha. Are you here?
Yep, I'm here.
Okay. So next, Andri will give a presentation about ice behavior under cyclic flexural loading. So please, Andri, go ahead.
Cannot share the screen. Can somebody unshare?
Yeah, I'm trying.
Yeah.
Just a second. Sorry
Yeah, it's a little bit slow.
Sorry, yeah.
Can you see my screen? Okay. So I'd like to present the work on fatigue of ice, basically behavior of ice under cyclic flexural loading. My name is Andri Murcha, and my co-authors are Erlen Schulson and Carl Renshaw, and our ice lab is based in Dartmouth College, Thayer School of Engineering. So why this topic is of interest? So we all know that ice covers in both Arctic and Antarctic are subjected to cyclic loading through the wave or tidal motion. And another example is that during the ice structure interaction, the loading the ice loading can be repetitive, and the question whether ice has the same properties after it experienced some loading, or does it change its properties and does it change its strengths? And when we do some evaluation or some modeling, do we have to take this into account? And in this work, I would like to focus on comparing the behavior of freshwater and saline ice or sea ice under this cyclic loading. So this work was experimental work, and we did grow ice in our tank, and we did grow it vertically, top down, unidirectionally, and that's the ice pack, about 1 meter in diameter and about 30 to maybe 40 centimeters thick. That's how it looked like after we grow it, and then we cut it with a chainsaw in the smaller ice blocks. And so then we try to characterize the ice. So on the left, you can see the both vertical and horizontal section of freshwater ice. And then in the middle, you can see the saline ice structure. And also we provided some vertical and horizontal thin sections of sea ice for comparison. And as you can see, they're very similar. So we indeed can say that we did grow columnar grain ice, S2. And we also checked the Z-axis orientation is good. So in this way, we confirmed that we got a S2 columnar grained ice. So as I mentioned, we did cut the ice into the blocks where columns were oriented vertically, and the grain size ranged from 3 to about 8 millimeters. And after we did cut some plates of ice, and you can see in blue, you can see the orientation. So then here's our test setup. So we use 4-point bending apparatus that we made. And as you can see, the plate, we would put the plate here and we could bend it up and down. And the middle part, two middle parts could move up and down, and the outer parts are rigid and don't move. And we could also measure the displacement, the LVDT of the middle part of the surface, and we did also measure the load with the load cell. And that's the photograph of the test setup. And so the way how we cycled our ice was we did it in reverse manner. So we first bent it in one direction and then in the other one. And in this way, we could calculate the outer fiber stress using the following equation. And so here are some first results that we obtained on freshwater ice. So we use, most of our tests were done, actually all our tests were done at -10 C centigrade. And we said, okay, let's try to choose. So let's first try to see the strengths of ice without cycling. So here's on the x-axis, we have number of cycles, and then the y-axis, we have flexural strengths that we got. So let's start with 0. Basically, we didn't cycle the ice, we just break it. And we got some measurements. And then the question was, how does it compare to the previous works that other authors did? And we compare this to the Timko O'Brien paper, where they summarized over 2,000 tests. And we see that our data fit pretty well the previous results. And the strength is about 1.7 MPa, plus minus some standard deviation. And then we were like, okay, let's try to cycle ice for some number of cycles. Let's try to apply 1, 2, 3, 4, 5,000, 10,000 cycles and see what's happening. And after we applied this number of cycles, we stop cycling and break the ice. And we noticed that the more cycles we apply, the stronger the material is getting, until some point somewhere around a few hundred cycles, and after which it seems that the strength's saturated. It's pretty interesting result. So the next we said, okay, so we know that we have to, in order to saturate, in order to get a saturated strengths, we need to cycle about 300 times. So, okay, we said for the all future tests, let's cycle for at least 300 times each sample. And then we started, let's try to vary the stress amplitude at which we cycle. And again, on the x-axis, we have cycle stress amplitude. On the y, we have the resultant strength. And we started with the low stress amplitude, something like 0.1, 0.2 MPa. And we started to go further and further. And for those who are wondering how we were able to get such a high stress amplitude at 2.5, which is quite higher than the original strengths of ice, is that we first cycled at lower stress amplitudes, and thus we strengthened the ice, and this allowed us to go even further and further. And that's the maximum we were able to go to, about 2.7 MPa, and which resulted at the strength of ice of 4 MPa. And this trend seems to be linear. And interesting that the similar evidence before was observed by David Cole back in 1990s, where he did a direct tension test, push-pull test on cylindrical ice samples. I think those were granular. And he mentioned that one of those resulted in 2 times stronger after cycling. And also some strengthening was observed by a group at Brown University, where they did a Brazilian test where they did compression only. So it's interesting that these results can be obtained at different loading conditions and different test type of setups. On the next slide, for comparison, we want to provide some data. I don't want to go into detail here, but we did some experiments on lake ice that we collected in the Arctic on Svalbard, and then we brought it to the lab at UNIS, and we did cycling of these samples. And the conditions, the loading conditions were slightly different. It was 3-point bending versus 4-point bending, and we also had a different size. But it's interesting that these new points in green, they align pretty nice with the previous results that we got on the laboratory grown ice, which gives some confirmation that it seems to be the feature not of the ice that we grow in the lab, but it's rather for any type of ice. And the next step was we grew sailing ice in our lab, which was similar to the sea ice, natural sea ice, with the salinity ranging somewhere from 3 ppt to about 6 ppt. And these new data are in red in this image. So we did follow exactly the same procedure as with the freshwater ice. And we do see that the strength again increases. The higher the stress amplitude, the greater the strength. There is some question that initially up to about 0.4 MPa, there's no significant strengthening here, and probably more work needed to confirm why this is happening. But after that, it seems to be that the slope of this strengthening slope for the sailing ice data is about the same as for the freshwater ice, which is pretty interesting that it seems that the sailing ice is not getting weaker under cyclic loading, but rather stronger, and behaves in the same way as freshwater ice. And so what does it all mean? And we're here dealing with the flexural strength. And we know that in bending, the one surface undergoes compressive stresses, the other one tensile. And we know that the strength, compressive strength is greater than tensile. So we have a tensile failure, and basically ice fails under tension. So we're dealing with a tensile type of tensile strength. And we have 2 possibilities. We have either crack nucleation that controls tensile strength, or crack propagation. And since the grain size is larger than some critical grain size, in our case it was a fraction of a centimeter, we have a crack nucleation problem, meaning that once the first crack nucleated, it propagated. And also in all our tests, we did not see any remnant cracks. So during cycling, we did not see any evidence of any remnant micro cracks. meaning that once the first crack nucleated, it propagated and failure occurred. So what are the reasons? What are the mechanisms here? And this could be either dislocation pileups and grain boundary sliding. And we try to do some analysis, and we think that what's happening there is that during cycling, we generate dislocation. And this dislocations, they serve sort of like a back stress. They pile up against some boundaries, against some obstacles, and they act as the internal stress against the applied stress, and thus they lead to an increased applied stress to make the failure. And this is somewhat similar as strain of work hardening in metals. That's what we think is happening. And it seems that the mechanism, based on the results that we obtained, that this strengthening curve looks similar for both freshwater and sailing ice. We think that this mechanism is the same for both fresh and sailing ice. Although one may argue that actually sailing ice, it has some pores, it's a weaker material, and there is a possibility that there is some development, some accumulation of damage, perhaps during cycling, and some other mechanism could be responsible, but so far we did not find any evidence of that. And that's why we suggest that the mechanism for strengthening is the same for both freshwater and sailing ice. And so conclusions such that the flexural strengths of both freshwater and sailing ice subsequent to cycling appears to scale linearly with the amplitude of cycling. The next one is that crack growth is not a significant contribution to fatigue life of both freshwater and sailing ice, which is different from other materials such as, for example, metals or other ceramic materials. And cyclic strengthening is attributed to the development of the internal stress that opposes the applied stress, and therefore it raises the level of the applied stress that is required to nucleate the crack. And then once the first crack nucleated, it propagates instantaneously. And the increase in flexural strengths of both freshwater ice and sailing ice, which is attributable to pre-failure load, basically the stress of cycling, is roughly equivalent. Yeah, thank you for the attention. If you have any questions, I would be happy to answer.
Thank you, Andrei. Really interesting presentation. Just somebody has.
Can I ask?
Yes, please go ahead.
Yeah, Andrei, I was thinking about this effect, and what I wanted to ask you that if you look on your beam when you cycle that, so then effective length of beam will be bigger than length of the beam in the rest. So then when you finish cycle it, so then you return beam in initial position, so and it make beam shorter. So therefore you will have compression stresses. What do you think?
So I mean during bending, the beam is getting longer. That's what you mean?
Yeah, because effective length of the beam is longer, stay in bended state. So therefore effective length, beam length became longer. Then you return that in initial position and it is compressed.
Yeah, so first I wanted to point out that we did not notice any significant plastic deformation. We're not able to measure that by our LVDT. So it means that the beam didn't change its shape. But do you think that this may affect the strengths that we measure?
Yeah, if it
ultimately?
is compressed, so of course, if it has this background stresses, because it became shorter, So then it will have some internal stresses in compression. Then when you bend that, the strength will be higher. Now I think that we may have something similar in fjord, where the ice is bended up and down by tide. And we measure stresses over the many cycles, and we discover some compression in unpredictable time. So it could be on different phases. So then I was thinking that
I
maybe
agree. I agree that this, what you're talking about, this creates some with internal stresses, compressive or something. When we return the beam to original position, it does have extra stresses inside, which I think prevent the easy crack nucleation.
Yeah, and it doesn't contradict your conclusions about dislocations. It may happen because of dislocations, but that I just was looking from another direction.
Yeah, because if we stretch the material, this volume has to come somehow, and there is a redistribution of dislocations, probably would generate new. So maybe that's all.
Yeah.
The one. It's a good idea, I think.
Yeah. Good. That was my comment. Yeah.
Yeah, I have kind of follow-up question for that. Did you do some thin sections or something like? Did you try to observe the structure of the ice kind of after the test when it broke? That did you notice some after the test structure?
Yeah, thank you. It's a very good question, and we did think about that, and we actually expected some change in microstructure after cycling. However, we analyzed many thin sections before and after, and there was no difference, between them. So there was no recrystallization in this. So, of course, we didn't have a possibility to look on the dislocation distribution where there is any different, because some transmission electron microscopy, for example, would be great, but the ice is not the best material to look at. If it was some metal, it would be a lot easier. So yeah, we did not find any change in microstructure.
Okay. Well,
the only thing what we saw some grain boundary sliding evidence. We did see some decohesion, some whitish features that appeared along the grain boundaries, which needs. So we did see this in the freshwater ice. We did not see this in saline ice because of opacity of the. But we didn't find a good explanation for that. What exactly causes this, or how this affects the strengths.
Okay. Well, thank you for interesting presentation.
Thank you.
Well, I guess we will see something in the future from this as well.
Yeah.
Okay, then next speaker, Polina Stogny, about the topic for the numerical modeling of the dynamic processes in the ice samples using the Ricci characteristic method. Please.
Good morning, ladies and gentlemen. Can you hear me and see my presentation? Yeah, okay, then I'll start. My name is Polina Stogny, and I'm very glad to present together with my colleagues Viktor Epifanov, Vasily Golubev, Katerina Beklemisheva, and Vladislav Myryaha, our work, the numerical modeling of dynamic processes in the ice samples using the grid characteristic method. This is the short plan of my presentation. First, I'll present the two problems solved in the work. Then I'll say a few words about the numerical method, the grid characteristic method for the solution of the problems. And then I'll present the results of the numerical modeling, the wave fields of the velocity module distribution, and the Cauchy stress tensor distribution in the models. And then I'll present the results of the comparison of the modeling results with the results obtained in the laboratory experiments. In this work, we explored two problems concerning ice models. The first problem was the problem for the ice of the truncated cone shape in the Laval nozzle for the two-dimensional case and three-dimensional case. We applied some load on the one side of the nozzle and then obtained some effects. And the next problem is the problem concerning the obtainment of the circularity of fracture inside the cubic ice sample after shock loading and unloading. So before presenting the results of modeling, I should say a few words about the determining equations. We used the linear elastic equations for modeling the ice medium, where rho is the density of the material, v is the velocity, t is the time, sigma is the Cauchy stress tensor, and lambda and mu are the Lamé parameters characterizing the characteristic properties of the material. We used the grid characteristic method of the third order of accuracy for the solution of the linear elastic equations. Here I present the grid characteristic method for the two-dimensional case, but the same presentation can be made for the three-dimensional case. It was made just for simplification. So we can present the system from the previous slide in the first form under number 1 in the matrix view. Then we split our system in coordinates and obtain the system under number 2. This system is hyperbolic, then we can present it in a view number 3, where omega x is the matrix made out of the eigenvectors of the matrix Ix, and lambda x is the matrix made out of the eigenvalues of the matrix Ix. And Ix, Iy are the matrices made out of the coefficients of the constant coefficients of the system from the previous slide. Then we make the variable change and obtain 5 independent equations, which are presented under number 5, which can be solved using different numerical schemes. We used the numerical scheme of Rosanov of the third order of accuracy. So now I'll turn to the modeling results for the first problem. We applied some force on the left side of the ice sample, which was put into the Laval nose for the two-dimensional case. The length of the sample was 50 centimeters and the height was 5 centimeters. The characteristic properties of the ice material are present in the slide. So this is the model. And then after some computations, we collected the distribution of the velocity module inside the ice sample with time and the analogical distribution of the Cauchy stress tensor inside the ice sample. And we can see that the stress which was applied on the left side of the ice sample, it spreads through the ice cone. And then we compared the results of the numerical modeling with the results of the laboratory experiment, where the ice sample in the Laval nose was put inside the polarized light, and we can see some thick line, which is under number 3 on the right picture, and we can see the same line, central line on the left picture, which is the characteristic line for the wave spread inside the Laval nose, and we can see a good coincidence between the results. And one more effect which we caught in our numerical experiment is the so-called cumulative effect. This is the velocity module distribution on the central part of the cone, and we can see the maximum of the velocity on the central axis of the ice cone. Then we carried out the similar experiment for the 3-dimensional case, but here we used again structured grids, but hexahedral grids, some kind of curved grids for modeling. The parameters of the model were the same, and the parameters of the ice medium were the same. And we again obtained the velocity module distribution, which have a very good coincidence with the laboratory experiments. And the next problem which we investigated is the problem of obtaining the circularity of fracture in the ice cube. We applied some loading on the ice sample, and the loading, the places of loading are marked with blue discs. This is the upper and the low sides of the ice cube. And then we unloaded the ice cube. We used the Tsai-Wu failure criterion for destruction in our numerical modeling. So we wanted to obtain a thin flat crack of a circular form, which was previously obtained in the laboratory experiment. So we tried to obtain it. So here are the results of the numerical modeling after application of some loading on the upper and lower sides of the ice cube. We do not use high amplitudes in order to collect just the wave fields, the distributions of the velocity module inside the ice cubes. And so here we can see no destruction. And then after application of shock unloading, we obtain destruction in the central part of the ice cube. This is the first part of the destruction, which is presented by several cracks. And after that, this is the second phase of the destruction, when the waves come from the from the back sides of the ice cube. They interfere, so we obtain some kind of disk crack presenting the destruction inside the ice cube. Here is a better view of the disk crack presenting the destruction, but still there are some additional cracks, fractures around the disk crack, and so we tried to avoid them, but without them we did not succeed to obtain the disk crack presenting the destruction. So this is again the view at an angle. So here we can better see the disk crack in the central part, and on the sides, on the left side and on the right side, there are some additional cracks of the destruction. This is the view from one side, and this is the view from above, where we can see the disk crack in the center and some fracture on the sides, on the left, on the right, from the crack. Here we can see the results of the laboratory experiment. The picture presents the disk crack in the central part of the ice sample, but there are no cracks around the ring destruction, which were obtained in the numerical experiment. So we made the hypothesis that the compression, which started before the shock unloading, led to the hardening of the central part of the sample, but still this question should be demands more exploration in future. Now I'll conclude my presentation. We presented the numerical solution for the two problems of formulation, for the problem of modeling the ice in the Laval nodes, and for the problem of obtaining the circularity of fracture inside the ice cube. For the solution of these problems, we used the grid characteristic method of the third order of accuracy. We obtained the results, some numerical results, and the results for the first problem had a good, rather good coincidence with the laboratory experiment, and the results for the second problem were not bad, but still they need more exploration. So thank you for attention, and now I'll be glad to answer all your questions.
Thank you, Polina. Really nice presentation. Does somebody in the room has some questions regarding the presentation? It seems that not. So I can ask something. So you, for this laboratory experiment, so how did you manufacture this? So you drilled some like hole, some centimeters into the ice cube, and then you put some like rod there, and then you try to tear it. Was that how you did it? I'm not totally sure. This picture, it looks like there's a small hole at the top and then at the bottom.
In the laboratory experiment, several loads were applied on the sides of the cubic ice, and nothing was drilled inside the ice. And so after some load and shock unloading, the disk crack appeared. And the problem can be in the boundary conditions or on the sides of the ice cube, because they should be almost ideal, because even one boundary condition on one side can destruct all the results, can lead to the failure of the results. So we are working on this problem.
Did you do several lab tests or just one? Because I think that usually if you test ice, the results might change depending on a case to another. So usually you want to do probably few so that you see that you accidentally didn't encounter something unpeculiarities.
I'm not ready to answer this question because I did the numerical experiment, several numerical experiments, and we tried to obtain this disk crack. And so that's why maybe there was a series of experiments, but still I cannot reply this question.
Okay, well, at least you got some cracks, so it's promising. So
yeah,
looks
thank you.
good. So then I think we can start to go for the next presentation. So next presenter is Bratislav Izimov about Brazilian test and tension strength of sea and freshwater ice. So please.
Good day, colleagues. Can you hear me
Yes.
and see my presentation? Okay, I'll start. The topic of my presentation is Brazilian test and tensile strength of the sea and freshwater ice. In this work, we discuss the use of the Brazilian test to study the strength characteristic of ice. The strength of ice at brittle fracture is due to the initiation and propagation of cracks. And the second part of my work is devoted to the analysis of the influence of wind cracks on the fracture process. Brazilian test is a simple indirect testing method to obtain the tensile strength of brittle material such as concrete, rock, and rock-like materials. In this test, a thin circular disk is diametrically compressed to failure. The compression induced tensile stress is normal to the vertical diameter, which are essentially constant over a region around the center. The indirect tensile strength is typically calculated based on the assumption that failure occurs at the point of the maximum tensile stress, that is, at the center of the disk. The strength of the ice at a brittle fracture is due to the initiation and propagation of cracks. Wind cracks are characteristic defects in material such as rocks and ice. Wind crack propagation is described by the stress driving crack model. Due to the shear stress, due to shear, tensile forces are generated along the sliding area, and the crack behaves like a normal pull-off cracks. This work describes the numerical modeling of rectangle samples weakened by one isolated wind crack under the action of compression force applied at the ends, and cylindrical samples in the Brazilian test for the analysis of mechanism characterizing the failure of samples. Yes, experiments. The experiments described below will help us to demonstrate how the Brazilian test may be applied to studying the strength characteristic of the fresh and seawater ice. Test of series of cylindrical ice samples of the same type by the Brazilian method gave an ambiguous picture of destruction, splitting of the sample into two equal parts along the compressed diameter. For CIs. On slide, a result of determining the tensile strength using the Bazilio test presented. Experimental results for CIs. Next slide, we analyze the experimental results. Stress evolution was performed according to the analytical solution of the circular disk stress problem. We consider a wind crack in the disk. The solution of the problem is the superposition of three stress fields: radial top stress field, radial bottom stress field, and compression tension. Consider a wind crack in a disk. There will be areas in the disk where for each placement of a platform, there will be enough friction force to press down the sliding area. These areas can be found analytically. These safe areas will be at the periphery of the disk. No cracks can form there. In the danger zone, it's necessary to exclude pole caps, load points, because another elastic solution, the Hertz contact problem applies there, which is not covered by the solution of this stress field. In the remaining area, it's necessary to take a crack no larger than the size of the grain, and take the size of the area according to this Anderson. 2L0 is equal the size of the grain. And the remaining area is the laser zone where the coefficient of intensity for the related crack is less than K1C. The paper Stepanova and Dolgich presents the result of experiments on circular samples. Figure on slide show the pattern of interferential bands in the disk loaded with 220 kilograms. Since the chrome determines the difference in the values of the principal stresses, they can be used to analyze whether or not the sliding area would be in the danger zone, if they were there. Numerical analysis. The problem considered here is two-dimensional. Figure on slide shows the configuration to be model. From an initially present crack of length 2L0, two tensile wind crack have grown to a length L, driven by a slide along the initial crack. The parameter are considered in the study for investigated the crack growth behavior is L is the wind crack length to initially present fracture length ratio. Angle phi, angle of inclination of the main crack to the axis X, and mu, friction coefficient of the sliding area. In numerical simulation of rectangular samples weakened by one isolated crack during the transition from the short to long Witten asymptotic, the picture of distribution of normal stresses on the sliding area changes. When the parameter L is greater than 1, this distribution of stresses corresponds to the problem of embedding a die in the elastic half plane. The figure on slide shows the distribution of normal stress for different value for parameter L. Wind crack propagation is described by the stress-driven crack model. Due to shear, tensile forces are generated along the slide, and the crack behaves like a normal pull-off crack in conjunction with condition. K1C is equal to K1. In numerical modeling, we obtain a non-zero value of the stress intensity factor K2, which corresponds to the behavior of longitudinal shear crack. Moreover, the value of coefficient K2 is of the same order as the value of the coefficient K1. The graph on slide shows the ratio of the coefficient for various parameters of numerical simulation. Validation of numerical modeling is applied by work of Lechner and Kachanov. This paper presents an overview of analytical formulas for calculating the stress intensity factor K1. On slide presents a comparison of numerical and analytical estimate for the K1. For short wind asymptotic, the obtained results are excellent. The difference between numerical and analytical values is less than 10%. For long wind asymptotic cracks, however, the value of the coefficient obtained by the numerical modeling differs strongly from the analytical one. This may be due to the fact that the large values of the parameter L, the stress distribution on the sliding area is more consistent with the stress distribution for the contact problem. But the maximum of normal stress is reached at the boundary of an elastic foundation. From a series of Brazilian tests on samples of the sea and freshwater ice, we address the application of the Brazilian test to study the strength characteristic of ice. The main conclusion are as follows. The experimental stress strain curves obtained during the Brazilian test of cylindrical ice samples gave an ambiguous picture of sample destruction, splitting of the sample into two parts. A problem with the experiments is that cracks are initiating and propagating from the loading point at the top of the cylinder. This is problem with the Brazilian test method has been discussed in the literature, and the researchers have tried to migrate by utilizing shaped strip pads at the contact loading regions or by flattening the contact area on the ice cylinders to some extent avoid the crack initiation stress concentration at the contact zone. Processing with photoelastic stress analysis to determine the position of the failure areas sites by wind crack. The frequency of isochrones will help us to determine the crack growth rate as long as it runs from the zone of concentration to the center, where everything is uniform. The main result obtained in the numerical simulation of samples weakened by a wind crack is wind crack propagation is described by stress-driven crack model. It has been assumed that the crack propagates like a normal pool of cracks. This assumption was not prompted by a numerical simulation of the problem. In numerical modeling, we obtain a non-zero value of stress intensity factor K2, which corresponds to the behavior of longitudinal shear crack. Thank you for your attention. I'm glad to ask a question.
Thank you, Rostislav. Does somebody in the room have some question regarding the presentation?
I may ask.
Please go ahead, Alexei.
So, yeah, so the question is numerical. What do you think about the influence of friction when the sample is compressed in Brazilian test? Because the question is because the value of tensile strengths measured were above 0.3 megapascal. So in a bigger test, we measured 0.1 megapascal. So, and then I'm thinking if it is scale effect or maybe friction could be important in Brazilian test. What do you think about the influence of friction in the loading point?
In a loading point for Brazilian test. Yes.
Yeah, because when you compress and to split samples, sample should have some displacement in horizontal direction.
Mm-hmm. I understand. Yeah. For experiment, influence on friction. Так. I'm so sorry.
What is the answer?
Yeah. No, friction is in Brazilian experiments. Friction will influence to the result. We can estimate the stress field by the elastic analytical solution.
Yeah, but in reality, you of course you have friction between steel and between ice in
Yes.
the loading point. So then it could be important. I think that it should be taken into account in the modeling. If you model crack propagation.
Numerical simulation. Yeah. Like in numerical modeling, we not obtain friction on a lot and sample, but we can consider another elastic solution for this problem. We can consider no, a shear stress to upload point.
Yeah. Okay, so then I don't have any more comments.
Yeah, probably following this question, how was the like I guess usually if you press spheric or cylindrical sample from like two flat bars in testing, it's probably slips quite easily. So how did you add some like friction on the surface, like with some sort of roughing the testing apparatus? So how did you manage to get the sample to stay on place? I mean, so that it doesn't start to slip.
Так, я понял. normal stress to the sliding area. No, friction force is in the disk will be areas in the disk where for each placement of the platform there will be enough friction force to press down the sliding area. In this area, the wind crack propagation is not continuous because the stress driving crack model is not working here.
Okay. Are there any further questions? Seems not so. Thank you, Rostislav. I think we have a few minutes in front of the schedule, but I think we can go to the last presentation of the session. So sorry for my bad pronunciation, Vyacheslav Bosnik has presentation about ice strengthening with stiffening techniques and chemical modification. So please go ahead.
Just moment, I must include my presentation. Oh. Опа. Опа.
Так вы же открыли ее презентацию, она была открыта уже.
Да, она открывалась, но она вот у меня закрылась.
Нажмите, пожалуйста, на квадратик. Вот рядом с крестиком левее есть квадратик.
Ага.
Да, на него.
О, все.
И теперь демонстрацию, ну, в смысле, слайд-шоу лучше включить, чтобы на полный экран было. F5, кажется.
F5.
Нет. Ну или в левом верхнем углу.
Сейчас. Тут не F5, а рюмочку нужно.
Ну да.
Oh, sorry, dear colleagues. Good morning, Mr. Chairman and the colleagues. It's pleasure for me to make a report on this conference in very difficult time. First of all, I must apologize for my poor English. Language has always been a big problem in my academic life, and I will read the text. My report is review our research related of the strengthening of ice by method of reinforcement and chemical modification of ice. First of all, I want to remember you about application ice in Arctic region. It is road and crossing which use ice as a construction materials. It is a place for takeoff and landing of helicopter and airplanes in Arctic. Ice into ship, which ship and coastal structure are unloading ice for premise, waves house, ice hotel and restaurant, and other things. Ice for artificial ice islands, for installation, drilling equipment and drilling operation article of island. And I want to demonstrate exclusive Russia experience, ice docks on the Lena River in Yakutsk. This method realized, as I know, realized only Russia. This scheme of deep ice built up. Maximum ice sinks on the Lena River is 115 centimeters, and in the place where of ships repair near 15 centimeters. If you depths in island, because atmosphere is very cold, the ice begin growth in bottom. This method give possible build docks why depth is 3 meters. Advantage and limitation of ice ice as an Arctic construction materials. Advantage: the raw materials resource is abundance and water in Arctic. Second, the energy resource is present of Arctic cold. And opinion, resource is a long cold period through the years in Arctic. What is a limitation? Low strength characteristic and brittleness in ice, limited temperature range of operation of ice and structure materials, high sensitive of strange properties of ice to the conditions of freezing and operation. I will discuss about this this position, and we research you about method improving on structure property of ice. First method, it is chemical modification. Ice, like metal, has granular structure, and its strength properties depends on the size and shape of grains. By adding certain chemicals, dopants, to the frozen water, the strength property of the ice can be just. For example, it is structure of ice and this of metal. It's one method. It's methods difficult used for product of sport ice. Ice reinforcement. The reinforcing object with high strength are industrial into the ice markets. The armature interacts with water molecule only near ice. Ice armature interface. Types of ice composite and fields. We have many type of composite, ice soil mix and another helium composite. But we in our presentation discuss dispersed field ice and low dimensional fields ice. It is fibers, fiber, non-woven meshes and films. Next slide. The investigation of many materials and for example, it is distillate water for first point, and another nanotube, carbon nanotube, vegetable material, modified you can see improve of strength and use and we find so that fiber reinforcement is more effective and we discuss about this object. All these pictures transform of ice object under external mechanical influence. Destruction of pure ice and reinforcements beams, composite with polymer fibers, and deformation curve on these pictures. Green curve, it is pure ice, and red and blue is it is it is composite material. You can see when reforms ice beams, the strength increase on 7 times and deformation in 15 times. It is for its results for ice reinforced by basalt fibers. Another type our investigation, it is destruction and deformation in cylinder. you can see as destruction ice, and this result reinforced cleaner, and it is picture demonstrate concentration of you can see when reinforcing cylinders soldiers, ice strength increase 4 times, and destruction is replaced by squashing. We use model calculation and destruction of ice cylinder under axial compression by the use discrete element method. It is a scheme of a model, and this experimental and this is a calculation model. You can see that this model calculation have quality and quantity between the model and experiment. For experimental deformation cube, first it is experimental, and this is calculation. And we conclude the model and direct elements quality and quantity described of distribution cylinder during compression. We find good conditions, optimal conditions for ice reinforcement beams with basalt fibers. First parameters, it is number of fibers in one layer. We find that optimal, it is cut 5 fibers on one lace. You can see increasing on before 5, and this not dependency. Layer tab high, and we find shows that destruction dependence of high of this layer. Number layers in ice beams, and optimal number 3 layers, and it is better which you locate layer in near bottom. And fiber length, number of layers, and concentration in ice beams. The next our investigation is ice beams reinforced with basalt nets. Basalt nets are used in road construction after chemical treatment, and this treatment give improve rigidity and hydrophobic. You can see result in destruction after our experiment, and basalt bottom view, you can see defects, and side view. we use not only industrial nets. We use laboratory nets without chemical treatment, and you can see that materials in laboratory have a very good result, and this industrial and this material. And a result of our experiment, hydrophobic treatment of fiber and meshes greatly impairs the strengthening properties in ice composite. On this slide, we demonstrated using chemical modification and reinforcement. When chemical modification is now practice regulate performance property of sport ice. When you include chemical dopant, we find this dopant located in intergranular space, foam or grain space, and may change structure of ice. This deformation cube of ice beams reinforced with basalt fibers, red cube, and sample combined reinforcements and chemical modification ice, dark cube. You see that combination and chemical modification in reinforcements increase the ability control of response property of ice. We have high criteria for ice behavior obtained in laboratory applied to large samples. It is very important for real application ice cream for practical in Arctic land. We made engineering test of dimensional ice composite. We construct equipment. He demonstrate during the landing his simulated left and the side view experiment approach for dynamic load test. He imitated aircraft contact with ice lens. And we use the product engineering test demonstration of ice composition.
Sorry to interrupt, but we are soon running out of time, so please come to conclusions in a few minutes.
Yes, thank you very much. Conclusion. Systematic studies of beams on cylinder freshwater ice related to created for strengthening ice composite by the reinforcements, its morphological concentration and topology in ice particles. The identify criteria are applicate not only laboratory scale model ice, but also for larger size subject, as shown by engineering test. It is established that combination of reinforcements and chemical modification of matrix can explain possibility controlling of operating properties of ice composite. The possibility of theoretical calculation of process of destruct of ice cylinder under axial composite by method of discrete elements is shown. Our dream is to implement of our knowledge for research in natural condition of fresh and seawater. We invited everyone to cooperation, and thank you for your attention, and sorry for my poor English. It's finished.
Thank you, Vyacheslav. I think the English was good. At least I think I understood everything. So no worries from that. Any I think we have time for one question from the room, or if somebody it seems that in YouTube there's no question. Alexei, you have questions?
Yeah, I may ask. So my question about, is it possible or somebody tried to make ice composite from seawater? Because fresh water in the Arctic, at least in our place, are usually frozen and not so much fresh water, but a lot of seawater. If we freeze seawater directly in the tank, we will get very saline ice. But if we want to make ice composite, what we will get from seawater?
Oh, dear professor, you know better than I that seawater, it is a very difficult object for investigation. We not investigate seawater, and we are now planning use our methods for fresh water in Siberian River, but we can investigate in sea ice only with cooperation with you.
Yeah. So that was not investigated yet, as far as is it correct that nobody tried to make ice composite from seawater?
No, now we have people which want to apply our investigation is in river water.
Yeah, I see. Thank you.
Okay, thank you, Vyacheslav, and all the other presenters. So that was about it for this session, I mean. So now it's short time for coffee break, and the next session will start at 12. So hope to see you around. Thank you very much. Okay. Hi again. Do we have the other presenters online, or do we miss somebody? So is the last presentation is video? We don't have actual presenter, or
Yeah, but I think we need to try sound in this video.
okay.
Do you hear the speaker's voice?
No, I didn't hear anything from the presentation.
Okay. I will play the audio from the video throughout my microphone. Maybe it will be better.
Okay.
Good morning. My name is Khabibul Nurdar. I'm a postgraduate student of Moscow State University. The topic of my report is theoretical and experimental investigation of fixed and beam bending.
Do you hear it?
Yeah, it's not the best, but I can hear it, so I can understand
Okay,
what is said.
okay.
So I think it's probably enough if nothing else can be done.
Okay. We have not first speaker, but it's time for us to start. Maybe Professor Buznik can report.
Yeah, do we have anybody? So we don't have anybody on waiting room or anything. No. Bus. Okay. Hello again, Vyacheslav. Do you have you're part of the first paper? Do you have the presentation for that, or do we have Golovin somewhere?
No, we have no presentation. And we have not speaker.
Okay. Yeah, so probably wait for a while if somebody comes, because then if somebody wants to jump between sessions, then they can kind of be online there. Or all the sessions are recorded, right? So everybody can kind of come back to the videos. For example, if I now start presenting that, then they can later come and see those, right?
Yes.
So probably we can then just go ahead and I will give my presentations, and then at the end we will play the video. Or if Golovin comes, then we jump. He or she can present give the presentation. But okay, so I will then go ahead with my presentation. So just a second. Okay, so I guess you can now see my screen. Okay, so good. Hello to everyone. So my name is Mikko Suominen, and I'm going to give a presentation about our Antarctic sea ice property measurements that we have done in the past. And co-authors are Liangliang Lu, Pentti Kujala from Aalto University, and Henriette Becker from Stellenbosch University, South Africa. And the content of the presentation is that I will shortly give you a background for our measurements, then general description of the voyages, how we collected the samples and did the measurements, and then some conclusions and discussion. So as a background, when we ever are designing a ship for ice operations, we need to have some knowledge of the ice properties. And in case of Antarctica, there's a need for ship operation because there are several research stations that need logistic support that are handled through sea transportation. But because of the remoteness, there's not so many ships going there yearly or annually. And then when the ship go there, then there's not so much measurements done on these drift sea ice outside the ice shelf itself. But because we need this knowledge, then we have been on board the SA Agulhas 2 since her maiden voyage 2012 in Antarctica along this South African National Antarctic Expedition voyage. So in some of these voyages, we have been doing mechanical and physical property measurements of the sea ice. So in this case, we now wanted to kind of give our data also for others use. So if there would be some data pool regarding flexural and compressive strength or the physical properties of ice, so that others can also have this knowledge. So generally, how voyages have been done is that usually the ship departs November, December of a year. Then it goes along the zero meridian towards Antarctica, and then when it reaches Antarctica, then there's some logistic operation near the Antarctic coast, and then around late December, early January, the ship goes then for what is called buoy run. So generally it visits South Georgia and South Sandwich Islands, and then return back to Antarctica mid or late January to do last remaining parts of the logistics, generally taking some stuff that needs to be taken out from Antarctica back to main continents. And then after all the logistics are done, then she starts the voyage back to the Cape Town. And this has been usually the kind of the general schedule of the voyage. However, in 2018-19, the visit she visited Weddell Sea as a part of this British Antarctic Survey expedition to Weddell Sea. And part of our researchers were also on board that voyage. Sorry, wrong button. Okay. So then usually along the during these voyages, the first ice is encountered around 60-degree latitude. So when the ship goes down in this December, the sea ice extension is up to 60 latitude. And usually in these latitudes, the ice is quite loose, or it's not so compact. But the kind of the thickness and the compaction increased towards the continent, and generally the severest condition for ship operation is near the Antarctic ice shelf. But then during the summer season, the sea ice generally quite vastly diminishes around the Antarctic. So then when the ship then returns to the start voyage back to South Africa in February, then usually the sea ice extension is only really close to the continent. So when the ship is on the voyage, then we have been able to get on the ice to do some sample collection and do mechanical property measurements. And generally the procedure has been that the scientists are lifted with a crane to the sea ice, so ice flows. Then we have been cutting the ice samples with the chainsaw from the ice field. And then we take the samples on board the vessel where we trim those. So for 3-point bending flexural strength, we usually trim these long narrow beams with the chainsaw, whereas for this compressive strength, we have been using bandsaw to trim the size of the size and dimensions of the sample to desired. And then when we have trimmed the samples, then generally we have been doing the flexural strength measurement through this exit to 3-point bending. Yes, generally the equation for that. And then also compressive strength, we have been measuring XC2, okay, there's typo, as an anaxial compressive strength. For density, we have been using two methods. When we talk about this flexural strength and compressive strength, we have been using the left-hand side equation for density, which is not exactly because the ice is so porous. It's not. We could also consider this as some sort of indication of porosity, because if there's clear air pockets, this kind of then indicates also those. So generally, we have been doing it so that we measure the dimensions of the sample, and then we measure the weight and kind of take the average density over this volume that we have defined. Then the 2018-19 measurements, we defined the density through this similar method that is used in ITTC guidelines. So generally we submerge the sample and measure the weights at different steps and determine the density through that. Then 2018-19 voyage, we also did some thin sections and measured the structure of the ice. So here are generally the property measurements and results from the flexural strength measurement. So the flexural strength has been in our measurement generally varied between 130 to 500 kilopascals. And we have been observed that the strength really follows the seasonal change. So generally when we measure the properties in late December, early January, the properties are closer to this 100 kilopascal. So really, ice is really weak. But then when we go towards the end of January, then the strengths start to increase because the temperature is usually getting lower at this time of a year in Southern Hemisphere. So then yeah, what we have been generally observed is that it really depends on the season. However, we should bear in mind that we have had some problems in flexural strength regarding in the measurement, so that because the thickness of the ice have prevented somewhat the measurements from the lower part. So we have been able to take sample from the top part mostly. So in this case, it generally is quite close to the air temperature, probably the surface that we measure. So this is has probably a bit more air temperature has a bit more influence on the measured properties than if we would be able to measure actually through the whole thickness of ice. Then compressive strength we have been measuring on the same locations where we have been measuring the flexural strength. And here we have plotted now the compressive strength against the density. So there's kind of, or as I said, these are now quite closely related to porosity. And but we can see that because the porosity has been really low in some cases, then usually the defined compressive strength has been also quite low. So we are talking about less than half megapascal compressive strength. And we have been doing these measurements in 2 directions. So generally horizontal and vertical. So vertical would now mean kind of a lot parallel to thickness, and horizontal normal to thickness direction of the ice. But generally similar trend can be seen that the density or porosity has quite strong influence on the compressive strength, which is quite reasonable and intuitive. Then besides sea ice, we have been doing some measurements with continent ice as well. The kind of goal in this was that we wanted to know kind of what is the condition of ice before it gets kind of the iceberg before it goes from the air to the sea. So this then measurement generally showed that most of the ice was actually quite porous, or it had like the structure looked more like this spheres glued to spheres frozen together. But again, here we only had samples from the relatively close to surface of the ice of the top of the ice shelf. So these were only up to, I think, 1.5 meters. I think was the highest depth or lowest depth that we could go, and then test the compressive strength. So these are not probably the ice would have been stronger, or the structure would have changed more if we would have been able to go deeper in this. But again, similar kind of trend that the compressive strength is really increasing along the porosity. Then 2019-18, we had more. We didn't do any these mechanical property measurements, but we had more like focus on the physical properties. So we measured the ice temperature, salinity, density, and then also grain size through this thin section measurement. And generally there were 4 instances that these measurements were done, and the samples were in this case not taken by this chainsaw, but we used the Kovacs ice coring drill to get the samples to extract the sample from the sea ice. And in this case, we also managed then to get deeper into the ice. So here are some of the results. So density and grain diameter. So in case of density, so now this was done through submersion. So you can see that the density is always close to 900, I would say. So it's quite, there's not so much air pockets probably in this case. So it represents ice densities as we would assume those. And it seems that the depth of the ice doesn't really change the density. So the density is quite constant through the thickness of ice. However, this when we measure the mean grain diameter, then there's quite clear influence of the depth. So when we go up till or kind of the grain sizes are quite small on the top surface, and when we go towards the bottom of the ice, the grain size increased as a function of the thickness. Quite intuitive as well for S2 ice. Then temperature, temperatures were measured right after extracting the samples on the ice field. So generally the samples were not taken anywhere, but just when the sample was gained on the surface of the ice, then with this COVAX drill, then we measured the temperature. And here you can see the temperature profile. So it seems that again, at the bottom, it doesn't really anymore go below minus 1.5 degrees Celsius, but on the surface you might have a bit lower temperatures. So at the top, generally the temperature is more affected by the air, and of course at the bottom, more about the temperature of the sea. Salinity also seemed to be lowest at the top surfaces and then increased towards the bottom. This is also quite intuitive, I would say. So as a summary, I would say we could say that the flexural strength has been varied between this 100 kilopascals to 500 kilopascals, and average have been round about 300. These are quite expected that we would get low flexural strength because of summer season and also high salinity of the sample. But again, here it should be bear in mind that this is now more close to the top level of the sea ice or surface of the sea ice, as we weren't able to get really deep in the ice. So if we would have been probably measuring with bit different methods in situ and could have determined the flexural strength to the whole thickness, then this could have been affected a little bit. Then compressive strength have been generally in average from 700 to 500 kilopascals. Vertical direction has been a bit stronger than horizontal direction, which is, I think, in line with other measurements or kind of earlier publications. And yeah, that was it. Then we have been doing quite a lot of collaboration during the measurement. So we would like to thank generally from funding the Finnish institutes giving us funding to do this. Then also we would like to acknowledge the SANAP expedition and Bedelsea expedition and our colleagues from Stellenbosch University and University of Cape Town who have been helping us conducting these measurements, and then special thanks to all these persons listed here for doing the measurements with us. So they have been part of our research group conducting these measurements. Thank you. Are there any questions? It seems that we don't have any questions, so probably can proceed to the next presentation, which is also given by me. Or do we have Golovin online?
No, Dmitry Golovin has not appeared yet. He had technical problems.
Okay. Then I can continue with my second presentation.
Okay. Sorry, Miko, we have a question in YouTube.
Okay. So hydrostatic weighting, so you mean this kind of submerging it? I think that it refers to that. So yeah, in voyage 2018-19, we did it so that we followed this ITTC guideline procedures. So in that case, the density is measured so that you first take a box of water, then you measure the weight of that, then you put the ice sample on the bucket, you take the second measurement, and then you submerge the sample and take the third measurement, and then you deduce the compressive density based on that. So if I quickly share again my screen. So generally with this equation we then define it. So first measurement with only water, second measurement when the ice cube is put in, third measurement when we measure the weight when the sample is just under the surface of the water, so fully submerged, and then we deduce the density based on that. Were there any further questions? Okay, do we
Miko,
have
Dmitry Golovin here? Like Alexei Shuklinov.
Okay, it seems that we're waiting. So probably I go forward with my second presentation, and then we can see if the others, we can solve the problem during that time. Okay, so my second presentation is about flexural strength of freshwater ice in Saimaa area. So Saimaa area is part of Finland or Eastern Finland. So here you can see the map of the Finland and then zoom in about the location where the Saimaa is located. So last year we did some, during this year we have been doing some measurements, and so that's about my presentation. So firstly, I will tell you about something about the background, then research question, our research plan, then results from the first campaign, then some discussion and conclusion and future work. So as a background, we have a new project called InFuture, or it has been ongoing few years now, which kind of aims to develop sustainable and efficient inland waterway transportation solutions. And within this project, we are going to do some model scale tests in Aalto ice tank. And in order to do model scale tests, we have to define the flexural strength. So we first tried to go through some literature, and yeah, we found that freshwater ice, the values for that has varied quite significantly, what you can find from the literature. So from half a megapascal to over 2 megapascal. And for this freshwater ice, there's no similar kind of calculation formulas. At least we weren't able to find as there would be for sea ice for this developed by a team called Brouwer. So you could, based on porosity, define or give indication for flexural strength. So then there's also some other differences that some researchers or some publications indicate that temperature wouldn't have that much effect on measured flexural strength of freshwater ice, and also the measurement method would have increased impact. So because of this, then we started to think that, okay, yeah, we need to go and define the flexural strength of Saimaa area ice, because we need to do the model scale test. But then when we contacted the local operators, they indicated that actually the ice conditions vary significantly within Saimaa area. And generally they said that the ice would be different by the color. So they said that because of the contaminants coming from the rivers, coming to the different lake areas, the color of ice would be different in different parts of Saimaa. So then generally that raised our interest that, okay, can this flexural strength vary in different parts of Saimaa because of these possible contaminants indicated by the local operators? And then what would be the effect of these physical and chemical factors to the flexural strength of ice? And then at the same time, we are very interested that, okay, let's check the effect of testing methods, but also that what would be then the seasonal variation, so that if the earlier measurements have indicated that the temperature wouldn't have that huge impact on the flexural strength of ice, then it would mean that this flexural strength shouldn't vary from the midwinter to the spring season. So we would like to define also that. And based on this, we then determined to have like a big measurement campaign. So do measurements in January, February, and March. And we determined to do it in 3 different areas based on these discussions with the local operators or pilots of Saimaa. So we defined areas in southern Saimaa, northwest and northeast areas. And then we decided that, okay, let's do flexural strength measurements through cantilever beam testing, 3-point and 4-point bending. And at the same time, we want to characterize the ice. So we want to define the structure of the ice and contaminants inside the ice, and also contaminants in the water. So this is generally then the schedule. So we started, I think this was first measurement was done on Monday. So we first came here in the southern part of Finland, Saimaa, on Monday, then do 3 consecutive days of measurements in southern part. Then we went to northeast area, did 2 measurement days there, and then went to northwest area to do 2 measurements for 2 additional days. And during the first campaign, we did flexural strength test through this cantilever beam testing and 3-point bending test. And yeah, oops, okay. So here is an example from this 3-point bending testing that we did. And then Okay, and here is an example from this cantilever beam testing. You can see the cantilever beam kind of goes here, and then when we push it, then you can see at the end the small crack. So we did this rounding of the root corners with this Kovacs drill to have it bit to kind of diminish the possible stress concentration as much as we could. From all these tests we did this, we also measured the displacement of the beam, and from that we defined the strain modulus. And as said, then also we defined the structure of the ice through this thin section testing, and then also defined the density of ice. So here are generally the equations then what we use for this different testing. The derivation can be found from the paper. General conditions during the measurements were during the first campaign quite the same. So generally the air temperature during the measurements was from -2 to +2, except on the last day we had -10 degrees. There were some wind, and sometimes it was snowing a bit. And generally regarding this ice itself and snow cover in southern part of Saimaa and the last location in northwest location, the ice and water were really clear. So actually on the picture here, the ice is actually right next to the hole. So there's actually, it's on the edge. So it was so clear that it was really hard to see where the ice stops and where the holes start. So it was really clear. And there was only like 0 to 5 centimeters of snow in these locations. However, when we went to northeast and northwest locations, the ice had clear impurities inside it, and then the water was also brownish, and there was 20 to 30 centimeters snow cover in this location. So then the results from the flexural strength measurements, generally the results showed that when we defined the flexural strength through this 3-point bending testing, it was roughly 1.3 times higher than with cantilever beam testing. And when we compare this to the results by Gao, 1977, these are quite at the same range. So you can, from the actual measurements, you can see that there is some variation how much the ratio is in each location, but as an average, it's 1.3. Then when we go to strain modulus, it seems that you can see that the strain modulus varies a bit depending on from which test type we defined this, but there's no like constant indication that which would result in higher or lower strain modulus. So it seems that this is really test independent, or that doesn't depend on the test. So, but this is generally in line also from the earlier research. So we generally wanted to just kind of check this, that does it have an impact that if we would use testing method for this. But now bear in mind that this was now the strain modulus has been defined from this bending, some sort of bending test. So we didn't define strain modulus from this how fast the vibrations or the acoustics would travel in ice. So it's generally testing method is kind of the same for strain modulus from strain modulus point of view. Then when we check the structure of ice, we noticed that we actually encountered two types of ice. So sometimes it was S2 ice, sometimes it was S1 ice, but in some occasions it was some sort of combination of these. So on the left-hand side, you can see there was some, on the very left, you can see the quite clear, it was S2 ice. But then in some cases, if you look left-hand side picture, right side picture, so C51, we actually had a case that it started as two ice, and then it kind of the orientation of the ice grains differed. So first it was like columnar downwards, and then it changed to columnar horizontal. So we don't really know what has happened there, but really interesting. Then in some cases on the right hand side, you can see this combination. So we had like this part of the ice was really clear, fine grained ice at the top, and then started to go columnar downwards, but then it had these really large inclusions of large grains. But these were all now done like fastly with fastly, I mean, we wanted to have some indication what was the structure of ice while we were doing this testing. So we actually at the same time collected samples to a freezer that was in the back of our van. So the idea is that we would go through more thorough structure analysis in our own lab at the university. So this is now ongoing work, and we hope that we manage to finish it early autumn. So then we can start comparing this more thoroughly. Then also we have taken the samples for this contaminant analysis. So as said, we didn't actually found that much variation in the strength between these locations in south and north, although the water was totally different color, but we have not yet been able to analyze the contaminant inside the ice. So that's another thing that we are going to do. Then also the analysis from the second and third campaign are ongoing. And in third campaign, we also did this kind of torsional test on the right upper corner. You can see we did this kind of L-shaped beam, and we then loaded that from the tip of the L, and then we could observe the torsional crack at the root or close to the root, which was few cases we managed to get quite nicely. It's like roughly 45-degree angle. So we would then, that would indicate that it was torsional, probably torsional related failure. So the analysis of this is also ongoing. And so yeah, that's about it. Then we also did have been doing some full-scale ice thickness measurements with this our stereo camera system, with this newly developed this loose bow concept, which is, so generally loose bow means that there's a motorized bow that can be operated by a tugboat, and the tugboat operates in Saimaa area with this loose bow. And last winter we installed our stereo camera system on board the bow to measure thickness alongside the operation of the vessel. So then we should get thickness profile from the Saimaa area. So we are trying to make more thorough mapping of the ice conditions in this area. And generally the work, we would like to acknowledge the support for this work. So this was done as a part of the Southeastern Finland Russia program. We are the project Future Potential of Inland Waters. So I would like to thank that. And then also we got some practical help from personnel in Finnpilot and this Finnish, in Finnish it's Väylä. I can't remember the abbreviation of this. What's the actual name of this FTIA, but the Väylä in Finnish. So they helped us defining the locations for the measurements and comment those, and then also practical help of Eetu Pajari and Marko Räisänen. Thank you. Are there any questions?
Mika, can I ask a question?
Yes.
Very interesting work and presentation. I have a question about the results where you compared the 3-point bending strengths and and cantilever strengths. So you
Yep.
mentioned it was 1.3. Just wondering if you know whether it's typical for ice and perhaps for other ceramic brittle materials, and whether you have idea the reason for this kind of 1.3 difference. Of course, I know that there is difference between tensile strength and bending strength about 1.7, because the volume under the maximum compression is different and is governed by the defect. Just wondering if you have any ideas.
If you mean that why it's exactly this number, I have no idea.
Okay.
I think it's generally, it has been just suggested that it would be because of that the change would be because of this root stresses. But in also in literature, it's suggested that this is only kind of for freshwater ice, that if you would go to seawater ice or saline ice, this effect would diminish. I haven't do the test, but that's what they said, that it's not so profound effect because of the somehow when you have some saline in the ice, then it start to behave a little bit more like ductile, so it's not as brittle. So we actually in one case, during second campaign, we actually had some problems doing the ex situ measurements for this 3-point bending, because we lifted the ice, and if you tapped it a little bit, you could immediately see crack just expanding all the directions. But in that case, it was -20 and it was winding quite hard wind. So I'm not sure if that was some sort of effect that it started to kind of immediately when we lifted it out from the water, there was probably some, I'm not sure, probably some thermal stresses coming because it came from the water to the really cold air. So it probably had some external stresses. So but that was really interesting. I had never seen that happening with ice when you a little bit tap it and you could see this really nice kind of expanse of cracks to all directions.
Mm-hmm. Okay, thank you. It's really interesting, and I didn't expect that this would be freshwater and sailing ice would behave differently in terms of this coefficient. That okay, thank you.
Okay, are there any further questions? Okay, I think we can then go for the other presentations. Do we have somebody from the first group about this acoustic and electromagnetic techniques for ice monitoring?
Yes.
Okay, then we could go for that presentation. So the presenter, please introduce yourself and go ahead.
Well, so how to put a presentation into Zoom?
On lower bar, you should have this green button, share screen.
Yes. Demonstration.
And when you click that, then it should show you options, which part you can. Okay, now we can see your presentation.
Acoustic and electromagnetic techniques for ice monitoring. Acoustic measurements include using piezoelectric transducers, and it's quite old technique. It has a lot of internal features which we can call a drawbacks. The first is it's elastic waves with quite short wavelengths compared to sample dimension. So that we have a lot of reflection from boundaries, many elastic modes, and it complicates the original signal. Then the piezoelectric transducer is a resonant object with a high quality factor around 100. It greatly enhances sensitivity, but significantly distorts original signal, so that we have no idea about its shape, and we can only measure its amplitude and time of arrival, and nothing more. If we go for electromagnetic emission, we take a couple of electrostatic antenna, that is a capacity sensor. It's in near field, so no wave effect in this setup, but it has quite low signal amplitude, so that the noise level is quite high. But it has very flat frequency amplitude characteristics, and its distortion, it distorts the signal to the very, very low, almost negligible level. So that we have a ability to see the shape of pulses, and can obtain some information from not only the amplitude, but much more wide set of characteristics of the signal. And the remote sensor is more convenient in just practical aspect of experimental setup. That is the table of comparison of acoustic and electromagnetic signals. More or less, I covered it in the previous. That is the experimental layout. We use two types of tests. It's a 3-point bending test and the indentation test with the sphere. With simultaneous recording of acoustic signal and electromagnetic signal using differential amplifier for electromagnetic emission and internal amplifier in piezo sensor, and then all that is provided to the National Instrument board and sent to computer. Ice samples is a distilled water samples freezing layer by layer. All experiments were carried out and at -10 centigrade. And we have two sets of samples. One is the pure ice, and the second is basalt fiber reinforced ice with a fiber diameter about 20 micrometers and strength about 1 gigapascal. There is the loading diagrams of pure ice on the left and reinforced ice on the right. As could be seen, the reinforced ice is 3 to 5 times higher critical stress are several times higher, and displacement to the fracture is many times higher, more than 10 times. And here is the signal of acoustic and electromagnetic emissions. Acoustic emission is a number of pulses. Here is the typical pulse shapes. All of them are the same in shape because the shape is determined by the transducer, but not by original signal. It has several modes. Energy is exchanged between these modes, and so we have these dampening oscillations, and it's a raw signal. We can rectify it. We can use various measures to increase sensitivity, like frequency filter, like rejection of wrong false determinations, and then reduce the threshold in threshold determination, threshold detection. Electric signals are much more diverse, and this is one of more or less steady and constantly arising signal shape. Electromagnetic emission has its sensor, its antenna, catches a lot of high frequency noise from the one side, and from the low side we have a lot of various leakages in this moist setup, so that we reduce the characteristic time RC of input circuit by using parallel resistor to differential amplifier, so that we have a characteristic time about 10 milliseconds, 10-15 milliseconds, so that we don't use, we shouldn't deal with accumulation of various signal in large time lengths. So that profile is just a delta function peak step. It's just a heavy side step, which then the tail and the dampening of the signal is artificial due to finite time of RC circuit at the input. But there are much more different signals. Here is some examples which greatly diverse from above and from each other. These signals appear at mostly at the initial stage of deformation, and at the last stage of deformation, almost all signals are just steps. And at the start of deformation, most signals are like these or these. And in the medium stage of deformation, they are mixed, and its number is lower than at the start or at the final stages, which is a bit strange, but it is there. And going for conclusions, we see that reinforcement of the ice with basalt fibers increases strength up to 5 times, with the relative part of basalt fibers being very low. Acoustic and electromagnetic emission in reinforced ice is many times higher, both in quantity and in signal amplitude, which is the proof that we see the real signal and not some measurement artifacts, because the difference is great in any aspect. In per time, per displacement, very significant differences. Some pulses in acoustic and electromagnetic channels are synchronized, so that we can ascribe them to some unknown event in the sample. But some are not, and that's not too strange, because both of the methods have its own bias. Surely we can see in electromagnetic emission channel only dipoles that are oriented perpendicular to the antennas. And in acoustic, we see only when something like micro cracks or any, or rather failure take place. But if some charges are just passing to some distance, we cannot see it in acoustic channel. So that these channels complement each other. And electromagnetic emission information content is possibly much higher, because we still can see its shape, and this shape, the shapes of the signals are very different, which surely can be ascribed to various mechanisms of deformation and fracture, but the nature of various pulses types is unknown yet, so it should be studied further. Thanks for your attention. That's all for this short brief.
Thank you, Dimitri. Does somebody in the room have one question? It seems not, so I can have one question probably. You said that you tested this for this basalt fibers, but it would if you would have some other stuff inside, other material inside the ice, like I think last session we had the presentation by Vyacheslav about this different kind of ingredients that could be put inside the ice. Would have you tested other kind of?
No, we haven't tested it yet, but the idea is very interesting. We are going to do something in this area. Basalt fibers has very high internal strength, so that we start from them. But surely some interesting results can be achieved with many other types of fillers, because probably it will not significantly increase the strength of the ice, but it significantly increase its maximal deformation, so that we will have a lot much more time and interesting physical processes in the deformation, so that we can expect a lot of emission to measure. I don't know whether it will be useful or not, but studying emission in such samples, but I think that the emission will be significantly higher than in pure ice, and so that yes, it's an interesting area to study.
Okay, thank you. I think we don't have any further questions in YouTube either, so thank you for the presentation. And was it so that the last presentation will be given as a video, or do we have the presenter here?
Good morning. My name is Khabibullah Nurdar, and I'm a postgraduate student of Moscow State University. The topic of my report is theoretical and experimental investigation of fixed and beam bending. The development of modern Arctic marine technologies requires a new ice breaking and transport vessels, fixed drilling rigs, and other special technical facilities for operation in ice conditions. At the same time, correct calculation of ice loads under different scenarios of interaction between ice fields and structures plays the most important role for operational safety assessment. Interactions of this kind are unique in a number of parameters. Investigation of failure and bearing capacity of a beam at a 3-point constraint bending provides an insight into the processes occurring during punching of ice flow by a concentrated load. Characteristic features of the bending process are the development of root and central cracks, the occurrence of spacing, transverse compressive forces that constrain the deformation process and lead to crack closure. The appearance of areas of compression and ice crushing in this compression areas. Field tests show that under concentrated loading, the bearing capacity of ice is exhausted at loads greater than the appearance of the first cracks. In order to study the characteristic feature, I proposed to investigate a floating ice plate of considerable size, in which two parallel cuts of equal lengths are made, forming a beam. The width of the beam being approximately equal to the thickness. During tests, the beam is loaded with a concentrated vertical load in the center, developed by a hydraulic cylinder at a constrained stroke rate. In full-scale experiments, multiple failure scenarios were observed. A typical deformation curve of ice being with fixed end in full-scale tests on sea ice is shown in figure. The length of the beam was approximately 6 times its height, and the loading was set by hydraulic cylinder rod stroke at a speed of 2 to 10 milliliter per minute. The initiation of development of cracks occurred at load less than to 10 force and the exhaustion of the beam carrying capacity at loads over 8. It is possible to observe on the graphics a sequence of the process, a linear section of deformation, appearance of central and two cracks, and the beam root, and then non-linear section of deformation where the material of the beam shows plastic properties. Thus, a multi-stage deformation pattern is observed in the beam test. Thus, balancing of the increasing load is provided by the expansion forces resulting from wedging, which cause the beam to be subjected to predominantly compressive stresses, relative to which the ice is very strong. The most characteristic feature is the constriction of the deformation, resulting in the phenomenon of slowed crack, followed by the stopping and closing of the crack tip. A special feature of 3D beam loading compared to cantilever beam bending is the constriction, the occurrence of longitudinal forces along with bending moment and transverse force. The longitudinal force N and the bending moment M arise as a response to kinematic connections. So Castellini's theorem is effective for calculation. When solving the problem, we assume that the root and central cracks have the same length and are the cracks of normal separation. We neglect that influence of transverse force in the embedment on the crack development. In order to compose the kinematic conditions for the coupling of the beam with the single regions, let us introduce to crack opening delta and then rotation of the banks theta. We will follow the method of Rice-Levy by representing the single regions as elastic elements, the yielding of which is determined from the solution of the strip cup problem. Then for each section of the beam, we can write first equation. Then for current, we can write the energy change associated with crack growth. The second condition, and where KD is intensity coefficient at the crack tip. Due to the superposition principle for the intensity coefficient, we can write the third equation, where sigma n and sigma m is the dimensionless crack is reduced stress, and omega is a dimensionless crack length parameter. Fm and Fn is a Knoll-Gauge function represented by Lagrange polynomials. From the equilibrium condition follows that the force M equal PL equal derived 8. Then we can use Castellini theorem and the formula of Paris to determine the generalized displacement. The system, due to the symmetry of the problem, we will understood as one derived for beam. Write down the elastic energy of the system. Equation 7. We also can find the generalized displacement of the single regions as equation 8 and 9. And from equation 6, we find the known value of reactive force, where zeta is a dimensionless parameter defining the proportion of the beam. If we use the force criterion for crack growth, KD equal K1C, condition 3 closes the problem of determining crack growth conditions. Also, since sigma and sigma m have different signs, if there are such proportion zeta of the beam and such a crack length, when the multiply before is sigma m 0, then at any value of load, the beam cannot be split apart by cracks. The phenomenon of crack closure arises. The family curves sigma and sigma m are plotted in left figure. Points also plotted there in which the condition for the minimum load is provided. The stationary value distinguishes two branches of the crack body state. Omega less omega m, the bending patch where the bending form of equilibrium prevails, and the propagation branch omega greater omega m. In right figure, the deformation of course of the strip at different notch lengths up to the limit state are plotted on the plane m theta. The straight line OB is the asymptote for the states of the spaces branch with the yielding lambda m min minimum force m equal minimum m theta defines the lower boundary of the crack instability. The problem also was modeled and solved by the finite element method. During the solution, the intensity coefficient KD and the yield strengths were determined. To determine KD, a numerical J integral method was used in the ANSYS mechanical pedal package. The mesh on the model beam was created with solid 186 elements, and from the graphs KD in omega, it can be deduced that first, there is such omega max at which the KD value is maximum. And the second, there is such omega that KD is 0. The considered problem of concentrated bending of solid beam in the elastic stage has an interesting qualitative feature. The danger of deep notches decreases with increasing depth until it disappears altogether. There is a limit length beyond which the crack cannot grow. The effect of crack closure is due to the occurrence of longitudinal force due to constriction. During the field test in Svea in March 2018, a series of bending tests were carried out on a beam with fixed end. To determine stress distribution, special geoconsensors were embedded in the beam and at key points based on pressure measurements in the test medium. The sensors consist of two circular stainless steel plates welded around the perimeter and separated by a narrow cavity filled with oil. The main purpose of the test with the GeoCon sensors was to determine the stress distribution during loading. The sensors C1 to C4 have an upper pressure limit of 1 megapascal. They were positioned near the line of maximum compression on the crack beam. nonlinear behavior. The merge test with Geocon census was conducted on 8 March 2018 on a floating ice sheet in a fjord near Svalbard. Ice thickness 0.6 meter, ice temperature -8, ice salinity 5.4 ppt. The central crack occurred under a load of 32 kilonewton, which allowed the bending stress strength of 330 kilopascal to be determined. The stress time curve associated with the SODI scenario is shown in figures. The voltage time curve according to FEM, finite element method simulation at the same location and orientation as the Geocon sensors is also shown in the figures. It can be seen that the ANSYS simulation show significantly lower stresses on S1 than the Geocon sensor measurements. The most reasonable interpretation is that ice exhibits both elastic and inelastic behavior, which must also be considered. Thank you for your attention.
Okay, thank you. Because this was video, I think we can't have any questions really regarding this because there's nobody to answer. So with that respect, I want to thank all the presenters for this session, all the technical support. And that was it for this session. And now there's a lunch break for 1 hour. So other sessions, all the sessions will continue after 1 hour. So depending on your time zone, I don't say any time when it will start, but after 1 hour we continue. Thank you.